In this lecture, we will cover the basics of hidden Markov models and how they're used to build acoustic models in speech recognition systems. Here's a quick recap of the statistical speech recognition formulation. Capital O refers to a sequence of acoustic feature vectors and corresponds to the speech signal. So you take your speech signal, break it up into small segments of speech here, which are referred to as speech frames. Each speech frame is typically of length 10 to 15 milliseconds, corresponds to 10 to 15 milliseconds of speech. And now you have a capital O, which is a sequence O1 to O capital T, where T is the number of speech frames in your speech signal. And each O sub I is a d-dimensional acoustic feature vector. Okay, so the ith speech frame is represented by OI, O sub I, and think of there being an acoustic feature vector extractor which acts on the speech frame and produces this d-dimensional vector which captures all the content in that particular speech frame. Okay, this is your observation vector, the sequence of observation vectors. And let W, capital W, denote a word sequence. So the ASR decoder has to solve the following optimization problem. That is, it needs to find the W, which maximizes this conditional probability, right? And we said that you could apply Bayes' rule and write this as the product of the likelihood of observing O given W, some word sequence W, times the probability of W itself. So this is the prior probability of the word sequence. And now we further kind of decompose this probability of O given W, because W is 2 cores of a unit. Each word is 2 cores of a unit to estimate this probability distribution. So we say, okay, let's introduce Q, where Q roughly corresponds to phones. Okay, so now probability of O given W can be written in terms of this marginalization over all sequences of phones which correspond to this word sequence. And now you have these 3 terms: probability of O given Q, probability of Q given W, and probability of W. And we saw last time in the first lecture that probability of O given Q is typically referred to as the acoustic model. So how do we compute this probability distribution? And this is where HMMs come into play, and we'll look at how HMMs can be used to estimate this particular probability distribution. All right, so an HMM is a generative model. Here is how a generative model of speech would look. So you start with the text in your utterance. So say that you said hello, the word hello. Now this could be represented as a sequence of phones. So the word hello is the sequence of phonemes h, l, o, right? So there's a sequence of 4 phonemes which corresponds to the word hello. Now, corresponding to each phoneme, I can have different hidden Markov models. So this is the HMM corresponding to HH. This is the HMM corresponding to EH. This is the HMM corresponding to the phone L. And this is the HMM corresponding to the phone O. Right, so now I have these 4 HMMs. And so then the generative model of speech would be that I have some speech signal, which is denoted by capital O. And I want to look at the probability of O given this word hello, right? And the fact that hello can be decomposed into this phone sequence, and each of the phones have this corresponding trained HMM. So say that I kind of break the speech signal into 4 segments. Okay, so say this is H, this is the A sound, this is L, and say this is the O sound. Okay, and then this I'm roughly going to say this is segment 1, segment 2, segment 3, and segment 4. So when I'm saying how do I compute probability of capital O given hello, I'm looking at the probability of, so here, of course, I'm assuming that I've been given this segmentation. So what is the probability of S1 given the phone her times the probability of S2 given the phone a probability of S3 given L times probability of S4 given O. And here, of course, I'm breaking this up as this product by making some conditional independence assumptions. Now, each of these probabilities, so say that S1 is of length some T1, right? So I can write probability of S1 given H, her phoneme, as the probability of, so it's essentially the probability of O1 to OT1 given that it's phone H, right? And similarly, this will be the second segment. So that's O T1 plus 1 all the way to O T1 plus T2 and so on. So here you're assuming that the length of the second segment is T2, right? Now, how do I, okay, now this is the question of interest. How do I compute these likelihoods? How do I compute this probability, and so on? So here, there's a condition on EH, right? And this is where HMMs are handy and gives us efficient algorithms to compute these probabilities. So let's now jump into it. What are hidden Markov models? So a lot of the figures and the notation also I'm borrowing from the chapter on hidden Markov models from one of the reference books that I have posted on Moodle. This is Speech and Language Processing by Dan Jarofsky and James Martin. So this draft is available free online. So you can refer to this particular chapter. Okay, before we dive deeper into hidden Markov models, let's kind of ease into it. So let's start with just what a simple first order Markov chain is. So here, a Markov chain can be defined using the following formulation. So you have a set of n states, which are denoted by Q1 to Qn. You have what's called a transition probability matrix. So here, each entry, A sub ij, represents the probability of transitioning from state I to state j. And because these are probabilities, all the outgoing transitions from state I, the probabilities of the outgoing transitions should sum to 1. So that is this particular expression, right? So all the sum over all j, A sub ij should be equal to 1 for every I, for every state I. And these entire set of probabilities can be written as a matrix, a transition probability matrix. And then you also have what is called an initial probability distribution over the states. So this is saying, okay, how probable is it that my sequence of observations starts from a particular state? Okay, so this is the probability that the Markov chain will start in a particular state I. So pi I defines that initial probability. And like it mentions here, for certain states, pi I could be 0, meaning that it's never possible to start in those particular states. And here again, this is a probability distribution. So the sum over all I pi I should be equal to 1. So here, this is an example of a Markov chain over weather states. Okay, and the vocabulary of these weather states is hot, cold, or warm. So you can see that the states themselves are labeled with these weather events. Okay, and now you have these transitions where from any state you can transition to any other state, right? Or you can stay in the same state using these self transitions. So this particular graph, now it gives you the probability of seeing any sequence of weather events where the weather events are drawn from this vocabulary, hot, cold, and warm. So this you can kind of leave as a short exercise. So how would you compute the probability of having seen the sequence, say hot, 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 or warm, hot, hot, or cold, hot, warm. Okay. So you can try and so this would just work out to be the product of different transition probabilities, but make sure that you're very comfortable with computing these probabilities. So here um, you can see that you can derive the probability of any sequence of weather events just by transitioning through these arcs, okay, from one state to another, and also taking into account the probability of starting at a particular state, which is defined by this pi vector. Okay, so now this is a first order Markov chain, and note here that the probability of transitioning to a particular state only depends on the current state. Okay, so if I'm at cold, the state cold, then the probability of transitioning to warm only depends on having been in the state cold in the previous time step. So I don't care about the states that were traversed in any of the previous time steps beyond just the last time step. Okay, so I'll formalize this notion um, more clearly when we actually define hidden Markov models. So this is a first order Markov chain. Now let's slowly transition to hidden Markov models. So you'll see here in this problem, you had weather events and your Markov chain comprised of states which were denoted by these weather events. Okay, so there's no distinction made between observations and anything else which is kept hidden. Okay, so the states are your observations. Okay, so this is a fully observable kind of setting. But in real life, there is this natural distinction between observations, that is what is available to you, and events of interest which are not necessarily observable. Okay, these are events which are hidden or latent, and you are interested in understanding distributions over these hidden variables of interest. So a very standard example, especially in NLP and speech, which is used which is used in conjunction with hidden Markov models, is part of speech tagging. Okay, so say that you have a sequence of words, so you have a sentence, and you want to find the underlying part of speech tags. So is this word a noun? Is this word a verb, and so on? Now, the observations given to you are only the word sequences. You don't know the underlying part of speech tags, right? And but you are interested in identifying what these part of speech tags are. But here again, there's a distinction between observations and this hidden variable of interest. So similarly in speech, the observations are going to be your speech signal, your acoustic feature vectors. Okay, so this is the O1 to O capital T. These are your observations. But you are interested in what could be the underlying phones, right, in this particular sequence of observations. And that is hidden. You don't have that information at the get-go. You only have these observations. So here, this kind of lays the context for formally defining the specification of HMMs. So as with Markov chains, you have a set of n states and you have transition probability matrix A, where each A sub ij is the transition probability from state I to state j. Now you have this sequence of observations, okay, as because now there's this distinction between the state sequence and an observation sequence, right? So these are your observations denoted by O1 to O capital T. And now you have another set of probabilities, which are referred to as emission probabilities or observation probabilities or observation likelihoods. Okay, and this is the probability of an observation O sub T being generated from a particular state I. Okay, so here this is denoted by B sub I of OT. So this is the probability of an observation OT being generated from a state I. Okay, so QT is equal to I. This is the probability. This is the emission probability. Okay, and So you can imagine you could, especially when these probability distributions are discrete, you can have an observation likelihood matrix, okay, which represents all the emission probabilities across all the states. And finally, like in the first order Markov chain, you have an initial probability distribution over all the states. Okay, this is the specification of an HMM. Here's a toy problem to illustrate the workings of a hidden Markov model. And this is due to Jason Eisner. So here the observations are the number of ice creams that someone eats per day. Okay, and the hidden variable of interest is the weather event. So whether it is hot or cold. So now the vocabulary has been reduced to 2. So you can see along with the transition probabilities over the states, you also have these emission probabilities. So what's the probability of someone having eaten 1 ice cream given that you're in the state hot, 2 ice creams given that you're in the state hot, and so on. So there are so your observations come from this vocabulary, which could be 1, 2, or 3, right? Similarly, you have an emission probability distribution when you're in the state cold. And then as with the first order Markov chains, you have an initial state distribution as well. Okay, so this is just a toy task. We will refer to this again when we describe some of the HMM algorithms. Now, there are 2 important assumptions which govern hidden Markov models. The first one is one we already described in the context of Markov chains, which is the first order Markov assumption. So what this says is the probability of a state Qi depends only on the previous state. Okay, so what is this particular formulation saying? That a state is conditionally independent of all the other states given the previous state. Okay, so Qi given Q1 to Qi minus 1 is the same as probability of Qi given Qi minus 1. Okay, it's conditionally independent of all the other states. So this is the first order Markov assumption. And the second important assumption that holds with HMMs is one of output independence. So what does this say? That the output observation OI, right, it depends only on the state Qi which produce the observation. So this is so here you're conditioning on everything other than OI essentially. So OI given Q1 to Qt and O1 to OT. And here you're saying that this is the same as the probability of OI given QI. This should be OI minus 1. Okay, this should be OI minus 1. And here you're saying that this is equal to probability of OI given QI. So an acoustic observation OI is conditionally independent of all the other observations, okay, once you are given the state that generated it. Okay, so and all the other states as well. Okay, so OI only depends on QI. This is a very useful independence assumption from a computational standpoint. But if you think a little about it, especially in the context of speech, is this really a meaningful assumption? So we are saying that the probability of having seen some OI at the ith speech frame is conditionally independent of all the previous observations, right? And only depends on the current state. That seems like a fairly limiting assumption to make, and it actually is. And then later on, when we cover other models, we look at how we can get around these independence assumptions that are made by HMMs. Okay, but this assumption makes our life a lot easier when we are trying to estimate the probabilities of the HMMs. Okay, so these are the 2 main governing assumptions that hold over hidden Markov models. There are 3 quintessential problems which hold for HMMs, and this is defined by Rabiner in his seminal tutorial on hidden Markov models, which I recommend that all of you go through. So here are the 3 problems. The first is, how do we determine the likelihood of a particular observation sequence given an HMM? How do we decode, meaning how do I discover or estimate the best hidden state sequence given an observation sequence. And the third problem is one of estimation. How do I actually learn the parameters, all the probabilities in an HMM, okay, given observation sequences, and having defined the set of states which are in the HMM. So once the HMM topology is also defined. So these are the three main problems. And this covers everything that is of interest to us, right, with respect to an HMM. How do I estimate the probabilities? Once I have these learned probabilities, how do I compute the likelihood? How do I find the best hidden state sequence given an observation sequence? So we look at these three problems in more detail. So here's the first problem, which is of computing the likelihood. So given an HMM, here I'm denoting the HMM by a lambda. So lambda is, so how do you fully specify an HMM? If you give me all the transition probabilities and all the emission probabilities, you're done, right? So this fully specifies an HMM. So these are the transition probability matrices and the observation probability matrices. So given lambda and an observation sequence O, what is the probability of O given lambda? That's the likelihood, right? And this we already, at the very beginning when we talked about the generative model of speech, this is exactly what we were trying to determine. How do I find this probability of O? And this, now we will look at the algorithm to do this efficiently. So let's go back to our toy problem setting, where you had these observations corresponding to the number of ice creams people ate on a certain day, and then the hidden states were referring to your weather events. Right now, say that the observation sequence that you have seen is 2-1-2. Okay, so someone ate two ice creams followed by one ice cream followed by two ice creams. Now, what's the, and this is your HMM. So what's the probability of having seen this sequence 2-1-2, right, given the HMM? Okay, so say that there's an oracle which tells you that the sequence of states that were traversed corresponding to 2-1-2 is actually hot, cold, hot. Okay, so then I'm interested in computing the probability of 2-1-2 given that I was in hot, cold, hot. Right? And this is just the probability of 2 given hot times the probability of 1 given cold times the probability of 2 given hot. And why is it that I'm able to factorize it nicely like this? Because of the independence assumptions that are made in my first order HMMs. Okay, so this, make sure that, and I'll leave this as a short homework exercise. So if you have, say, O1 to, say, some OT given Q1 to QT, you can write this as just the product of these conditional probabilities OT given QT. Okay, so you can factorize this probability as the product of just these emission probabilities. So here, note that each of these are emission or observation probabilities. And this factorization, make sure that you're able to justify it to yourself. Why am I able to write this particular probability as this product of emission probabilities? It's because of the conditional independence assumptions that we make in HMMs. Okay, so this is good, except I don't have such an oracle which tells me that the sequence of states that were traversed are HCH and so on, right? The whole point is that I don't know what the sequence of states are. I only have this sequence of observations, right? So what I want to do ideally is marginalize over all possible sequences of states that I could have transitioned through, okay, and which gave me this particular sequence of observations 2-1-2. Okay, so what I ideally want to do is I want to sum over the probability of 212. Okay, so here by Q, I'm referring to the state sequence, right, that was traversed corresponding to 212. So here, one important point to note that at each state, you're emitting one observation, which means that the length of the state sequence that is traversed is the same as the length of the observation sequence. Okay, this is not a strict requirement, but this is the setting in which we will work, okay, for all speech systems. So the number of states that are traversed is identical to the number of observations in your observation sequence. Okay, so how many such state sequences exist within this summation? So there are two possible states, and then there are three observations, right? So there are 8 possibilities for the state sequence. So here, so it could be probability of 212, and you can start from HHH plus the probability of 212 comma HHC and so on, all the way to probability of 212 CCC, right? So there are 8 state sequences, and that is this is the enumeration of all the state sequences, and you need to sum over all of them to find the probability of 212, right? Except this seems very, very tedious, and this can kind of exponentially grow, right, with an increasing number of states and with increasing number of time steps. And this capital T, especially for speech, the length of your observation sequence will be fairly high, because recall, each OI corresponds to a speech frame, right? And a speech frame is just a few milliseconds long. And if you're uttering an entire sentence, that's maybe of the order of 1 or 2 seconds. And so then capital T is in the hundreds. Okay, so then if you actually want to enumerate all the possible state sequences that could have been traversed, this blows up very quickly. Okay, so we need a more efficient way of computing the probability of an observation sequence. So in comes the forward algorithm. Okay, so it turns out there's a very nice dynamic programming algorithm which gets us the answer. And this is of the order of n square t, okay, the complexity of this algorithm, where n is the number of states in your HMM and t is the length of your sequence, the observation sequence. So here is one way to kind of visualize the forward algorithm. You can build what is known as a forward trellis, okay, and how is this trellis set up? On the x-axis are your observations. Okay, so O1 to here T, capital T is 3, so you have 3 observations on the x-axis. And the y-axis, you list all your states, okay, the HMM states. So here you have 2 states, which you're going to denote as 1 and 2, just for kind of ease of notation. And you also have this pi, which is the initial state probabilities, right? Now, corresponding to each cell in the trellis, you have this quantity, which is referred to as a forward probability. Okay, so alpha Tj is the probability of landing in the state J at time step T and having seen the observation sequence O1 to OT, okay, given a particular HMM specification. So that's exactly this probability. So it's the joint probability of having seen the observation sequence O1 to OT and landing in state J at time step T. Okay, so this is referred to as the forward probability, and it is denoted by alpha sub T of J. So this, internalize this notation. So at each cell of this trellis, you can compute the forward probabilities. Okay, and as you progress into the along the observation sequence, you're essentially computing the probability of all possible paths that could have been taken to reach that particular state. So for example, if you look at this state, here alpha 2, alpha sub 2 of 2 means that you have landed in state 2 at time step 2, and you have observed the sequence of observations O1 and O2, right? So there are two ways, there are two paths that you could have traversed. You could have started at the start state, transition to H, and then transition to the state. Or you could have started here at the start state, you could have transitioned to C, and then you could have transitioned to this H state. Okay, so there are two paths, and you need to sum the probabilities of both these paths to compute this forward probability. So it turns out, so here this, so you might probably see where we're going with this. So there is a nice recursive formulation of the forward probability, and you can accumulate these forward probabilities just by computing the forward probabilities in the previous time step. Okay, and here is the recursive form. So alpha sub t of j can be written as sum over all I. Here I is the I is indexing your states. Alpha sub t minus 1 of I, okay, times the transition probability of transitioning from state I to state j times the emission probability at state j of the observation OT. Okay, so this is the probability of emitting OT at state j. Okay, so this is the recursive formulation. And this recursive formulation can actually be derived in a fairly straightforward manner. So let's try and do that. And later on, when we introduce another quantity called the backward probability, you could try and derive this on your own. So this is the forward probability. You're saying that this is the probability of O1 to OT, comma QT equal to J given lambda, right? So this, you can write this as summation over I, the probability of O1 to OT, QT is equal to J, comma, QT minus 1 is equal to I. This is condition given lambda, right? So I'm just going to drop this given lambda. So assume, that holds in all the following expressions as well. So here I'm just summing over all the possible states in the previous time step. So this you can write as summation I, the probability of OT given. So I'm going to use a little bit of shorthand. So I'm going to say 1 to t minus 1, comma, qt equal to j, comma, qt minus 1 equal to I, times the probability of O1 to t minus 1, comma, qt is equal to j, comma, qt minus 1 is equal to I. Okay, so this is just base rule, right? So OT given O1 to t minus 1. Yeah, hopefully this is clear. Now I'm going to simplify this further using the HMM assumptions. So what can I say about this first term? This is nothing but OT given QT equal to J, right? Because of our observation independence assumption times, yeah, what can I say further? That it's the probability of, so now I'm going to rewrite this joint over O1 to t minus 1, comma qt minus 1. I'm going to write as probability of qt equal to j given qt minus 1 equal to I times the probability of qt minus 1 equal to I, comma O1 to t minus 1. So again, I just decompose this using Bayes rule. So this is probability of OT given qt equal to j times, what can I say about this probability? Again, this would just be qt equal to j given qt minus 1 equal to I, because the state only depends on the previous state. It's conditionally independent of everything else, right? Times this particular quantity. But what is this quantity? It's alpha t minus 1 of I, right? So this is the forward probability at time step t minus 1 and landing in state I at this t minus 1th time step. That's exactly what this probability is, right? So here's my recursive form. So I've derived it. This is my b sub j of OT. This is aij, and this is alpha t minus 1 of I. So I've kind of derived this particular recursive formulation. Okay, so here is a visualization of the forward recursion. So here at this particular state qj, you're trying to find the forward probability alpha sub t of j. So you sum over all I, alpha t minus 1 of I, and then you have the transition probability. So here you've computed these forward probabilities at all the states in the previous time step. And then you're looking at this additional transition probability of going from that state to the current state, okay, which is denoted by A1j, 2j, and so on. And then you have this additional emission probability, right? The probability of having emitted OT at the state qj. So this is my recursion. Okay, so here is the forward algorithm. So there's a base case as in any other recursion. So here you have alpha 1 of j, which is just pi j. So recall pi j is your initial state probabilities times the probability of having emitted O1 when you're in state j. Okay, so that is alpha 1 of j. And then this is the recursive form, which we already derived. And so when do you terminate? When you have derived the forward probabilities for all the states at time step capital T, and then you sum over all of these forward probabilities, that gives you the probability of the entire, of having observed the entire observation sequence, capital O. Okay, so this is the forward algorithm, which helps you compute the likelihood. So that was the likelihood estimation problem for HMMs. Now let's look at the second interesting problem, which is that of decoding. Okay, and this is something that is very related to the final ASR decoding problem, because we are given an observation sequence, and what we're most interested in is to find the most likely word sequence, right? So here that translates to finding the most probable sequence of states given an observation sequence and given a HMM, which is parameterized as lambda. Okay, so that's the decoding problem. Here, note the distinction as opposed to the previous likelihood problem where I wanted to compute the likelihood of having seen the entire observation sequence. Here, I only care about finding the best hidden state sequence, okay, the most likely hidden state sequence. Okay, how do I solve this problem? Turns out the solution to this problem looks a lot like the forward probability computations, except instead of summing over probabilities, we only consider the max probabilities, okay, because we are interested in identifying the most likely sequence of states given an observation sequence. So here now we'll define this new quantity, which we'll refer to as the Viterbi path probability. Okay, so this decoding algorithm, the one which is used to identify the best state sequence, is famously known as the Viterbi algorithm. Okay. Okay, so here's this Viterbi path probability. What is it? It's the probability that the HMM is in some state J after having seen the first T observations, right, and passing through the most probable state sequence Q1 to Qt minus 1. So that is the Viterbi path probability, okay, because here you're looking at the probability which is maximized by Q1 to Qt minus 1. So you want the most probable state sequence Q1 to Qt minus 1. Okay, and like in the forward algorithm, even in the Viterbi algorithm, you can compute these Viterbi path probabilities using a simple recursive form. Okay, and this can be derived using kind of very similar tricks that we use to derive the recursion for the forward algorithm. So I'll leave this as a short exercise that you can work out on your own time. Okay, so here is the Viterbi trellis, just like you had a forward trellis. Now you can construct a Viterbi trellis where the x-axis and the y-axis are exactly the same. But now, corresponding to each cell in this trellis, you will have these Viterbi path probability values, right? So now let's look at the Viterbi path probability value corresponding to this particular state. Okay, this is denoted by state 2, and you're at time step 2. So here, the best path to this particular state 2 is coming from some state I in the previous time step. Here, there are only two possibilities. It either came from state 1 or state 2. So what is the algorithm saying? That you'll take the best path up to a particular I, right? And then there is one hop. So if you're at this particular I, there is one hop here. If you're at this particular I, there is one hop here, right? And for this, so what is the probability of having taken this hop? Okay, what is the probability of this hop? It's the probability of emitting this observation O2 and moving to this particular state 2, conditioned on being in state I. So let me say that again. What is the kind of, think of it almost as a cost. What is the cost of making this particular hop? So I've taken the best path up to a state I in the previous time step, and then I have to make this one hop. What is the cost of having taken that hop? It's the probability of emitting O2 at this time step 2, and this transition probability of transitioning into state 2 conditioned on being in state I in the previous time step. So what is that exactly? It will be Aij times Bjot, right? It's the product of the transition probability of going from state I to state J times the emission probability of having emitted OT in time step in while you're sitting in state J at time step T, right? So that is the cost of taking this hop. And then the probability, the best path probability comes from the Viterbi path probability that you have already computed for each state I at time step T minus 1. Okay, and then you find the maximum value, which is accumulated for all these paths. Okay, and find the max out of these, and that is the value which is assigned to Vt of j. Remember, because we only care about the best path coming into j. So this is the Viterbi algorithm. Here is the algorithm kind of outlined formally. Again, you'll see similarities to the forward algorithm, except now you have an additional quantity that you're maintaining, which is a back pointer, right? Because you're at the end of the Viterbi algorithm, you'd like to identify the best sequence of states which corresponds to the observation, and so you want these backtrace pointers. So here the recursion we already saw on the previous slide, and here this is just keeping track of where this kind of transition happened, right, from the previous time step. So this is the argmax overall I, Vt minus 1 of I. Okay, so what was the